I'm Zahra Mohammadnazari. Okay, good. Yep, amazing. Thank you. Okay, hi everyone. I'm Zahra Mohammadnazari. I'm based in Coventry University. I'm a PhD candidate and assistant lecturer in Coventry University Center for Business and Society Service. And this is a study that we conducted with some fellow colleagues across the world, and I've got the privilege to present it here. Unfortunately, my colleagues couldn't attend this fabulous seminar, and I sincerely thank the hosts and organizers of this seminar to giving this the opportunity to present this work. Hopefully you'll enjoy it. Okay, so we'll get to the title. We have got hybrid machine learning, a meta-heuristic model for sustainable, I think this doesn't work, for sustainable agri-food production and supply chain planning under water scarcity. So, thank you, good. Okay, so as the name gives itself, so we're working in the supply chain. So what kind of supply chain is agricultural supply chain? We're utilizing OR techniques, operations research techniques, and also some machine learning techniques. And we're going to elevate it using meta-heuristic models to actually bring some productivity and proliferate some actions. We've got some sections to this presentation. First of all, I'm going to just go over the research problem and the why to this research, the significance to this research. We'll just have a quick list review, and we'll jump to the methodology ASAP, and I'm going to have again a glance of result and discussion and conclusion metric alongside. So let's get to the problem definition and introduction. This is the supply chain that we're working on. So this is the agricultural supply chain. We have one big issue in the agricultural industry, and this is pertinent to the water scarcity. Okay, so we're dealing in some parts of the world which are not actually limited. So let's say in big parts we're dealing with basically precipitation, reduction in precipitation, and excessive water usage. So this has led both of these factors has led the global food industry into some crisis and challenges. So it's actually reciprocal and it's a mutual relationship. So when we're dealing with water challenges, water crises, we're actually observing some reduction in the food production. The food industry in itself, the agricultural industry, the food production, the food industry in itself is actually dealing with some carbon emission challenges, and they're trying to walk on the path of carbon neutrality, but it hasn't been so successful in that way. So we're seeing pollutants all over the supply chain, from harvest, cultivation, to the very end, through the transportations to reach the end customer. So to tackle such complex issues, a predictive model in the first stage has been developed to estimate the amount of water required for food production to address the water scarcity challenge. And this model takes into account such factors such as global water crisis data, climate change-induced evaporation rates, and groundwater depletion rates. In the second stage of our model, we're developing an operations research model, a two-objective quant model, which considers, let me jump into this slide to show you, go back, because I need this picture. Okay, so this model, the OR model, considers the time which is required for the crop in this time. Do we need to give the crop to grow and etc. to reach the cultivation phase could vary from one crop to the other. So we have different products to actually combine and ship and go and make them go through this process. We're dealing with different crops. The crops then move ahead to the facilities, to the processing stage. In the factories, they're getting processed. We have also different vehicles in this design supply chains to transport crops from fields to the processing facilities. Then, after the processing stage gets finished, they move to the cross-dock to get. They need to get combined. We're trying to lower the lead time and also, again, reduce the transportation time, etc. And then finally, we'll push them toward the demand point. So we have different truck types. We have each truck has got different storage capacity, and we're considering also the carbon which is produced in our transportation actually stage, and the carbon and the pollutants also which are created in the cultivation stage. So we're addressing environmental sustainability by calculating the CO2 emission during the dispatching process, and also in the processing factories, cross-docking, and actually the cultivation stage. Moving ahead to the lit review, so we did our lit review in 3 major streams, which were actually momentous to this research. The first one was the global water crisis. The second one was green sustainability and green supply chain, just implementing green supply chain. And the last one was basically cross-docking, because we improved our network design using cross-docking to increase the lead time and just basically have better shipping. So let's go to our methodology and the models that we have utilized. So we have a 2-stage model. In the first stage, we're predicting the water consumption, how much water we need for different crops to basically grow and cultivate them. And the output for the first stage, the output for our machine learning model gets injected into the OR model to tell us how many trucks we need, when do we need to ship them, and where our trucks should be located, where should we build our facilities to actually smooth out the whole process. In the first stage, we're using PSO, particle storm optimization, in order to basically extract some features which impact the water scarcity. And I'll just present results just in a moment or so. Okay, so we're using PSO. We're also using neural network models, which are enhanced by genetic algorithm, some metaheuristic models. The results are compared, and the best one was genetic algorithms, which with the least basically. So neural network. Okay, thank you. Okay, so PSO helps us to extract some features, and some neural networks, CNN and GRU, which are improved using GA, helps us to elevate this model. In the second stage of the whole methodology, which is our OR model, we've developed a 4-echelon supply chain network. In the first echelon, we're trying to maximize the crop yields, minimizing environmental pollution. When I say environmental pollution, I mean the waste in this stage, as well as the carbon which is emitted, so the CO2 emission. And in the second and third echelon, we're dealing with the transportation and processing phase in the facilities. In the fourth echelon, we're sending them off to the retailers or the end customers. So, okay, so just a glance of our models. I'll move ahead. A glance of the models, basically. I think you're all aware of genetic PSO and just our CNN GRU gated recurrent unit and convolutional neural network model. I don't go over the modeling itself. So we'll come to the results when it's been implemented and what did we reach in the end. So at first, it's momentous to mention the results of the. It's momentous to mention the results of the PSO, the factors which impact the water consumption. So based on the results, we have wind speed, highest and lowest temperature, relative humidity, sunny hours, total monthly rainfall, average soil temperature as the most influential factors. PSO also basically limited the impact, basically skipped some of the factors because they had minimal impact. And those factors were wind direction, number of fog reports, and maximum hourly precipitation and sea surface temperature. So this is our PSO results. We also improved, as I said, we improved our CNN GRU model using genetic algorithm, and we compared their functionality using mean square error, mean absolute error, goodness for fit, R squared, and a root mean square error, RMSE. So So just elaborating on the results and what we have achieved at the end of this study and who do we present this study to. I need to discuss the fact that CNN GRU algorithm achieved a lower value in MSE, MAE, and RMSE, as you see in this table. And you see the numbers, so I don't need to reiterate them again. So moreover, the R squared, the goodness for fit, has got the higher value, which surpassed the performance of other models. Okay. We'll come to the presentation, the managerial insights, and just handing over the results to the decision makers. We found out that when it comes to also the final and end result of this model, we find out that the cross-checking was quite beneficial for the decision makers. Especially, it helped out with the metrics, improving supply chain responsiveness and enhance the overall efficiency. So managers could focus on optimizing cross-checking operations by efficiently scheduling inbound and outbound trucks. We also managed to reduce the idle time in the cross-checking stage and minimizing the empty vehicle journeys. So I'll just wrap everything up. I just want to mention some more. So I think my time is up, isn't it? Okay. So I'll just give it to you. If you want to dig deep, if you want to drill down into this study, you can find it. In here, yeah. It is published by Resources, Environment and Sustainability by Elsevier. So you can just drill down, have a look, and just looking forward to chat with you in the networking session. Hope you enjoyed it.
Does anyone have a question before we move on?
Could you just say a bit, I might have missed it, about what cross-docking entails?
Yes, in the cross-stacking stage, we're basically cross-stacking has got so many similarities to hub, okay, to hub location. We're consolidating all the crops that are coming from different facilities into one, let's say, one storage, and we're just shipping them out from that storage to the retailers, to the end customers. There are so many actually fruits to having and incorporating cross-stacking into the supply chain, such as basically reducing the transportation time, reducing the empty storage of the trucks, and also improving the vehicle routing problem. Yeah, so just we can have a chat. I don't want to just occupy more of your time. Yes. So,
Thank you very much. Great.